Good morning. Thank you very much for being here. I'm very happy to be here. My name is Mark. As it was mentioned, I'm better known as Large Cardinal, although more of an extra large cardinal these days. So I'm going to talk to you about advanced hardware attacks for the working hacker. Who here is a working hacker? Quite a few people, right? Okay, good. Who here likes hardware hacking? Oh, brilliant. Who here has done a large amount or a small amount or any amount of hardware hacking? Okay, good. So some of this you will see and then you'll go, oh, I know that. And then hopefully after that point, you'll be learning something, okay? But first of all, I'm going to give you an introduction to what I do. I'm going to give you an overview of the IoT ecosystem as I see it. I have a rather different view from some people, so hopefully it's going to be interesting. Then we're going to go over some actual attacks. Okay, I'm going to cover over what I think are interesting attacks that not many people know about or that aren't talked about very much. Okay, so hopefully this is going to give you a good overview as to what's actually going on, kind of in the world of breaking silicon and microchips, and that kind of thing. And then I'm going to give you some overview, maybe some strategies for trying to fix this stuff. Like how do we actually go about remediating all this kind of thing, okay? And then lastly, Kirchhoffs Principle and IoT. So I mentioned I'm going to talk about an ecosystem. This, I'm going to claim, is the ecosystem that you will see in most of your testing, okay? You will have, I hope you can see this, you will have some sort of user PC or smartphone, okay? And that will give you some sort of access to information, generally over the internet, to some hosted service, a cloud service generally these days. 5 or 6 years ago, we would have said, a hosted service run by the company, now everything's in the cloud. Okay, they just moved the problem to someone else's computer, effectively. But hey, so this is kind of what we see a lot. Who kind of agrees that this is a kind of a general model? You know, you have tested something on here, exactly. So we understand this picture really, really well. Okay, we understand all the transports. We understand Wi-Fi. We understand GSM. We've hacked Wi-Fi. We've hacked GSM. In hacking or trying to hack WPA3, we found new attacks on WPA2, for example, that came out last week. And we understand this model really, really well, okay? Because this is all very familiar stuff, okay? When we add an IoT device, it changes to this, okay? Remember, the problem with IoT is the I, Internet of Things. We want our kettles, for some reason, to talk over the internet. Okay? I need, I'm told, an app to control my kettle. Okay? I need the app so that I know what temperature it's at and when it's boiled. From China or from the next room. Okay? Somehow we've been convinced this is a good thing. And I do think that the connected world is something that is inevitable, but look at what it actually requires from a technological standpoint. Okay? What you're being asked to secure, because we are security people, is a device that talks Bluetooth to a smartphone, maybe Wi-Fi, might set up its own hotspot to talk to a user PC, and almost certainly will talk either via a mobile phone or directly over the internet to a cloud service. Okay? We're suddenly expanding the attack surface considerably when you look at the actual transports that are in play. We're expanding the attack surface and we're making our lives a lot harder from a security perspective. Okay? Bear in mind, we're also asking these devices to run lots and lots of code, and secure code is very heavy. I have a slide from a previous talk which is all about the Linux random number generator, followed by the quote, and you're expecting this to run on an Arduino? Okay? It's not going to work. Okay? We are trying to find better solutions. But also we're finding that there are more problems in IoT that we can sort of have a look at. So this is my favorite example now of IoT gone completely wrong. Alright? The Taplok is now, for me, the canonical example of how you mess it up. Because there's kids in the room. Okay? Taplok was the world's first smart fingerprint lock with a Zamac 3 aluminium zinc alloy casing. Zamac 3 sounds good, doesn't it? Do you know what it was for? I got this from, I think it was Dave or Andy at PTP. The Zamac 3 was designed to be a heavy-feeling, high-precision, die-cast model-making material. Okay? It melts at around less than 400 degrees C, and as you were there at the BSides, you saw a demo of a blowtorch taking care of the lock very easily. Okay? Likewise, it had BLE, Bluetooth Low Energy. Everything's got BLE. Why? Because it's really easy to implement. It's really straightforward to implement. It's very, very easy to make it work. Okay? However, they really messed it up. You took the MAC address, you gave it to the Bluetooth device, and it unlocked. Quote from last night, it unlocked faster through the exploit than it did through the app. All right? And the cloud API, you could just get data out, including location data, because the mobile phone app sent the location data with the unlock commands associated with the lock, okay? To quote, I think this is feeding back a little bit. We'll move it down a little bit, it's fine, there we go. Okay, to quote from PTP, Taplok already knew about the issues, but they continue to sell the lock on Amazon and have failed to make customers aware. I can't think of any term but immoral to describe this. It's an abuse of trust. I agree. So basically, they had this wonderful theater, this wonderful illusion of security. Okay? They created this kind of way of approaching the problem that said, we are the best, clearly, and they didn't. They weren't. They were one of the worst. Okay? This is how we are messing it up in IoT. They rushed to market, they didn't think about security, and this was for a security product. That's the best part of all this. It was a security product. Okay? So, moving on, what I'm not going to cover in this talk is stuff you probably already know, okay? I'm not going to tell you how to use UART. Who's got UART on a router or something? Who's done that kind of stuff? Brilliant. Who's used it to find RCE in the web application? Okay? Because you can. Set your payloads to be an RCE that will send a string out. You can script this in Python. If you want the example code, I will send it to someone. I'll put it online, maybe later. I'll clean it up first. I'm very, self-conscious about my code. So you can use, you build a simple web crawler, and what you do is you just have it send payloads over Python to every endpoint, and then you just have it send a string, a random string, to as an RCE payload, but you send it to the serial port, and then you read that out over UART. Okay? You do that, you have RCE, you do it on a bug bounty, you get money. Done. Win. See? Easy. There are better ways of using this stuff. We're told, oh yeah, you get UART, you get a root shell. That's not a hack. Okay, if I get into someone's house and I can solder on a UART port, they found me already, okay? If that's the attack vector, then I'm not worrying about the attacks, okay? However, we cover this kind of stuff a lot when we talk about hardware hacking. Putting firmware off with SPI, who's done this? Quite a few people, I would imagine. Brilliant. How to reverse engineer that, that's all well documented. Also electronics, I'm not going to teach you electronics, but if you want to learn, Elkam Tuff, Mikhail Zhalovsky, has a really good Electronics for Geeks page, okay? Really, really good. Can thoroughly recommend, okay? Thoroughly recommend. What I want to talk about is attacks on cryptography, attacks on firmware protections, and how fault injection attacks work. Okay? I want to be able to cover off how we are going to attack these things in new and interesting ways. Okay? So, here's what we're going to do. I'm going to start off by looking at some CRP bypasses. If you saw Cyber-Given's talk at BSidesLee's, there's a lot of overlap. Okay? So, code readout protection is very, very straightforward. Okay, we are basically trying to lock down the firmware from being read. To do that, you normally use something like a security bit. If the bit is set, then the firmware isn't read out. This applies to microcontrollers, not microprocessors, difference being microprocessors tend to have external flash and external ROM. So reading it off is a matter of removing the chip, putting it onto a breakout board and reading the flash off. Okay, or using eMMC hacks, or doing sort of stuff like that. On a microcontroller, the flash is integrated; it's actually on the silicon die. So what you have to do is you have to work a lot harder to actually get it out. All right. So you set these bits. So to prevent you from resetting these bits with a little bit of ultraviolet light, okay, which is how, if you ever work with EPROMs and you have to take the tape off and flash it and then put it back on, if you've ever done that, it still works, okay? But to stop you doing that, they did this. They put some metal coverings over it, okay? I mean, that's fixed, right? That's done. I can't hack that, can I? Does anyone know this? Does anyone not know this? Just flip it. 45 degrees will let the light reflect from the bottom up to the metal plate. Metal is reflective. It will then it will then commence to reset the bit. And here is Bunny actually doing the attack. Okay? It works. Okay? Simple stuff like this. Right? How else can we do it? LDR register readout attack on an NRF 51822. So this was documented very well. I'll put my slides online somewhere. This was found by Include Security. So for those of you not familiar overly with ARM instructions, because it's RISC, it doesn't let you talk directly to memory. You have to load and store data. Okay? So the load instruction is very, very important, and you will always find it. all right? Because you'll always find it, it's a nice little target to have a look at on some microchips. So the flash is locked on these chips. It says, no, you're not allowed to read the flash, no. But you have debug access. So what you do is use a script like this. This will work over OpenOCD. And all it does is it just sets the program counter to where you've located the LDR instruction. What LDR does is it dereferences the value in here, it's in register 3. Okay, dereferences that as a memory address and then puts the answer into R4, which means you just step through all of the possible addresses and you read the firmware out. Okay, it takes a while, but it works really well. Simple script like this bypasses code readout protection on this. Interestingly enough, the NRF5.2 series isn't vulnerable to this, if I remember correctly. Okay, so they did actually fix it, but it took going up to the next generation of chips. These are still used. These are in the BBC Micro, if I remember rightly. These chips are everywhere. Okay. Another well-known attack now is a thing called the cold bootstepping attack. I know I'm rushing through some of this, maybe it feels, but I don't want to dwell too much on the details because I want to really cover off that these things work. Okay? And I really want to get to the DPA stuff and the more sort of involved mathematics therein. So CRP does not always protect memory. Okay? On the STM32 F051, who's using an STM32 chip? A few people? Yeah, they're kind of cool chips, you know, they work really well. Nice ARM cores in them, very easy to get a hold of, very cheap, very useful. And they have this little bug, certainly on this one, probably on others as well, but I haven't had the time to really go through and check. I think some others are doing this. Where what you can do is you can actually attack the memory if the firmware does a kind of a self-check, like a CRC32. Just a consistency check. If it does that, it loads all of the bytes into memory. That memory can be read over debug. Okay? If that sounds bad, that's because it is. Alright? What does that mean? It means that, put simply, you can just bypass this control by finding where it does a CRC32 check, halting it there, and then pulling out the value, and then then resetting it, letting it run again to the next value, and pulling it out, reset it, let it go to the one after that. So you have to do the check many, many thousands of times. So it does take a while to get the data out, but it really does work, okay? It's a very workable attack. But what if debug is disabled? Well, there's an interesting bug. STM32s have a number of ways, actually, across the whole series for disabling debug, okay? The canonical way on most of the chips that you'll find is they actually turn on the clock for GPIO on bank A. So the debug pins are actually on GPIO bank A. When debug is enabled, then it runs debug through those pins. Alright? However, when you disable debug, and this is when you use things like STM32 CubeMX, which is one of the software packages for generating code bases, when you run this, what it does is it actually turns around and goes, okay, I'm going to enable the clock on these pins for GPIO, and that'll stop the debug kicking in. Okay? If that sounds like it's a fairly haphazard workaround, that's because it is, and it's a glitch away from actually being turned off there. But there's a more interesting thing on the STM32 F103, also known better as the blue pill. Okay? The blue pill has the capability of oops, that is it. That's me. The blue pill has the capability of actually being having its debug enabled and disabled by 2 bits across 2 bytes. Okay? The way that it works is if these 2 bytes at OF18, I think. Yeah, there we are. You can see it up there. At OF18 are set to 8062, then debug will be disabled. Okay? Oops, it is it. That's feeding back. That's fine. Goes on the other side. Anyway, so basically if those bits and bytes are set to these values, then it will disable debug, right? But that's not necessarily a protection, okay? What you can do is you can actually turn around and go, right, let's put it into boot mode, so the bootloader will run. Boot mode will then allow us to get the firmware off. We can patch out the firmware and then load it back on. And you can do this for the other disabling as well. You just patch out the function that is turning on the clock for GPIO bank A. Okay? You turn these things off, you've re-enabled debug. Why? Because there's a bootloader. It's effectively not a fix, basically. Okay? These things are not implemented very well. Alright? I was going to do a demo of this, but I've actually lent my stuff to a friend of mine, so I'm not going to do it here because it's in a different room somewhere. However, if you want to see more of these with demos and everything, then please go and watch Cybergibbon's talk, Andrew Tierney. There, he gave a talk at B-Sides Leeds, which I may or may not be involved with. I may or may not be the organizer. Shall I switch for that? Okay. Hello. I may or may not be the organizer of B-Sides Leeds. I'm totally the organizer of B-Sides Leeds. So he gave a really good talk there, and it was actually fantastic. And if you want to go and see these things in depth and in great detail, he runs through with demos of all of these and a few more as well. So that's a really, really good talk of these attacks, and it really runs through in great detail how they work and how they work really effectively. Okay? By the way, if you can't hear me, just start making this motion, I'll know what you mean. So what else can we do to these? Well, we have a microchip. It relies on certain things, such as power, or a clock signal, or not being messed with by people like me. So what we're going to do is I'm going to show you a few attacks that use glitching in new and interesting ways, okay? This attack is from Chris Galinsky. Chris Galinsky gave this talk at Recon 2016. The talk is actually really, really good, and he shows how you can use voltage fault injection to actually get the firmware out, or no, to kick it into bootloader mode, which then gives you the firmware, okay? The way that it works is, you'll see on the lower left the reset to application. So if you reset the chip and it runs into its actual main code, the power trace looks like this. However, if you reset to bootloader, it looks like this. Okay? So we want this, we don't want this, if that makes sense. Okay? How do we do it? Well, we use a voltage fault injection, or a glitch, as they're often called. Okay? A friend of mine's got this great phrase, the glitch in your security matrix fault injection attacks. Because that's what they do. They are very effective when used properly. Okay? So voltage fault injection is when you take the power either all the way down and you rely on the natural capacitance of the chip to just let it ride a little bit before you power it back up. But you lower the power enough that it actually has a problem. It has a little bit of a moment. And then it causes it to glitch in a way that it wasn't programmed to. You can also do this through clocks as well. A clock works through a rising edge, okay? So if you have a rising edge and a square wave like this, and then you take the square wave and you inject another rising edge, you will cause a problem in the chip, okay? What that means you can do is it means you can actually introduce unexpected behavior by just messing with the clock. So your one instruction will begin while it's running in the background. The glitch will cause another instruction to begin out of time and out of synchronization. And that means that so if it's like getting the security bit, for example, and then you glitch the clock, it might actually cause it to fall out and not return the security bits properly, which would default to being open, by the way, okay? And that's what we saw here. So Galinsky found that on the LPC 1343, the chip had 4 levels of protection, CRP level 1, 2, and 3, and also no ISP. And these were well defined, okay? The values were well defined. So OX 11223344, I think it was, would mean CRP level 1, okay? Whereas OX 22446688 would mean CRP level 2. It was very, very well defined. But if those bytes were anything else, that meant there was no protection. In that situation, a glitch works really well, okay? Because what you have is the ability to say, right, if I can get it to not read properly and to read in a way that it isn't supposed to, then it will default to open, right? And that's just what he did. So he used, I think it was a Max 4619 switch switch package. What it does is it lets you have microsecond switching between 2 pins. And he had 3.3 volts, the operating voltage on one pin, and then he had 1.2 volts, which is a brownout voltage for the chip, on the other pin. So if you took it like below 1.3, I think he showed a video where it just went down, and then at that level it went, nope, and the chip just shut off. Okay, so what you do is you send it to a voltage level where it's unstable. Other things you might do is, because I had a friend of mine who's an electrical engineer say, yeah, but what about my capacitors? And I just said, well, they're coming off the PCB, aren't they? You know, he didn't quite think that I'm going to mess with your board. I'm going to, hack it. I'm going to cause you problems by, sort of manipulating the physical nature of the board so that I can actually hack it. Okay? And then he took it to that voltage and he got the trace that you see here, which means it went into bootloader without the security bits. Okay? This is a viable, workable attack. It is reliable, it is repeatable, it works. Your code is not protected on these chips. Interestingly enough, the USB bootloader doesn't have this problem. The USB bootloader actually has a defined value saying, if you are set with this value, then you have no protection. Okay? And that's effectively one of the fixes that you can make. So this is a very reliable attack. But this attack is something that's absolutely spectacular. So Micah Scott, better known as Scanline, did this really amazing work on getting the firmware out of, I think it was a Wacom tablet with the pen, with the little pens and drawing things. It's brilliant. It's a 36-minute YouTube video, I think. It is absolutely worth your time to watch, okay? What she did was she developed this. So this is an Atmega microprocessor with a little USB chip, a Max 3421EE USB controller. What that does is it handles all the USB hardware for you, okay? It takes SPI in, SPI we know and understand, that's good, and out the other side it sends USB. But it lets you record, and it's two-way communication, so it lets you record what's going on the USB stack. What that means is, with this particular board, we can control the USB stack, and because it's designed to be used with a chip whisperer, who's heard of a chip whisperer? But who's used one? Well, you can come have a go later. And I'm going to do a demo in a little bit. But it plugs directly into the board, it's got all the right pinouts, and it lets the chip whisperer control the USB stack. What that means is we were able to do the USB handshake with the device and then work out how to glitch it. And the video shows you the process of glitching. The problem of a glitch is twofold. There's the when and the how long. Okay? When do you glitch and how do you glitch? Do you glitch for several microseconds? Do you glitch for longer? Do you glitch in all the way into the milliseconds? No, you'll never do that, by the way, okay? But what you do is you have this kind of zoning in process, which is the thing that you never see in the talks, because it's boring, put simply, okay? It's just watching someone just do this. The Chip Whisperer does have a lot of software built into it to help you out. And again, Micah Scott's video shows you how that process works, which is really nice to see. It isn't just, here's the result, it's, here's the result, and also here's how I got there. Okay, so it's a particularly good example. But also, it's just like, it's called the Face Whisperer because the Face Dancer, who's heard of this? A few people? Yeah? The Face Dancer uses the same chip. Only it has an MSP430 to actually do the SPI control and handles the USB over an FTDI serial chip. So, this is a brilliant, brilliant attack. What it allowed it to do was glitch it in such a way that when it went to fetch its version number for the USB traffic coming back, okay, so it would all chips report their version numbers or some other data about themselves to the host. When it went to fetch the version number, it just went and then had a moment and then dumped the firmware into a USB reply. Right? Because it dereferenced the pointer and it just went through everything. How did she find it? She just scrolled through and looked for the really big packet. Right? There was this USB packet of several kilobytes. Oh, look, it's the firmware. Winning. Okay? When you actually get it working, these things are actually very straightforward. Okay? When they don't work, they're infuriating and time-consuming, and you end up wanting to hit something. Not in a bad way. Okay? This stuff does take a bit of practice. It does take a lot of work. But Scanline's video on this is really worth a watch because it gives you a really good insight as well as to what's going on. So this is what I mean by glitching. It's practical, it's workable, and that's what I want to change people's minds about. These are not theoretical attacks. Yes, quite a few of them come out of a university. Cambridge, for one, has a group with lots of this kind of thing going on. But I think Lancaster's doing something as well, I'm not sure. But it's workable, it's real world. This stuff works. Now we're going to go on to DPA. DPA is one of my favorite things in the whole wide world. Okay, so if you don't like this, you hate me. You don't. It's fine. I'm being dramatic. Power line analysis. Who's heard of power line analysis? Brilliant. Okay, let's have a look at it then. So, determining bits of an RSA key by power line analysis. Yes, you can do it. What is an RSA key? Just tell me what it is. It's an exponent. So if you have 2 to the 64 or 2 to the 53, the 53 is the key in RSA, the 2 is the base. It'll never be 2, trust me, it'll never be 2, it'll break. Okay? But the idea is that it's just an exponent. Exponents make numbers really, 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 really big. Okay? So we have come up with ways of optimizing actually doing exponentiation. And the most common one is called the square multiplying method. So you read the bits of the exponent, here the bits of the RSA key, and if it's a 0, you just do a square. And if it's a 1, you do a square and then a multiply. That's what that pseudocode is trying to show you. So that's basically here. If it's you always do the square and then occasionally you'll do the multiply. All right? But the correlation between these operations on a chip and the power consumption is really strong. Okay? So you can easily identify what the power traces which power traces are which operation. Okay? So the way you would make it work is, here you might read off, I'm going to get square, 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 multiply, square, multiply, square, multiply, square, square, multiply, as an operation. That gives me the bits of the key, because of this direct correlation between power consumption and what data you're processing. Okay? This works. This is workable. There are papers. All of my slides, as much as I can, have links to papers which will give you more information so that you can sort of go away and read on this. This is only an overview just to show you that these things are workable. You're working hackers. I want to show you that you can do this, and it's not that hard to tool up. It takes a bit of learning, yeah. You have to go and learn a bit of electronics, but it's fully workable. It's practical. Power line analysis is really fun. Okay, and this is differential power line analysis, aka magic. All right. So I call it magic because that's how it's described when I show people that. They're like, "That's magic." It's like, yeah, I know, right? Okay. So the way that it works, here's a kind of an overview. The general overview of DPA is this: traces are gathered. So what we do is we perform some operation, some encryption operation. Right. This is targeting AES. It was originally done on DES. And the aim was to break the DES encryption on RFID cards. Okay, that's where it was first used. But then they realized that actually any or most block ciphers that use an S box, I will explain these terms, will actually be vulnerable to these attacks. And AES is vulnerable to this kind of attack. So what you do is you make some measurements, you take a load of measurements of power traces of the actual encryption, and you record the plaintext, ciphertext, what went in and what came back out again. The aim is that you're going to make some sort of assumption about these traces, and then you're going to do some testing. Okay? Remember, the key part here, there is a direct correlation between what operations are running, what key bits are being read, and the amount of power that will be consumed to read them. Alright? The way the Chip Whisperer does this, by the way, is it has a really, really clean, if you want to come and have a look at it, there's some lovely circuitry here, really clean power sources going in, and then on the other side of a resistor, that's where it actually takes the measurement. So between those two, those resistors are called shunt resistors. And what that lets you get is a really solid measurement of how the power is being consumed. Alright? So you make a guess. You then sort all the traces based on the data that you understand, okay? And then you make some sort of decision. Let's run through this in some detail. Windel Cipher, named after Riemann and Damon, won the NIST competition in 2000. It is a hardware-optimized, relatively easy to implement encryption cipher that has a lot of really good features, okay? It's a block mode cipher, which means that basically this is only half the story. The other story is how it propagates over the data. Okay, but this isn't a cryptography lecture. This is power analysis. This is to give you an overview of how it works, so that you can understand how the algorithm works at the end. All right. So sub-bytes is where you actually change out the bytes through an S box. An S box is a non-linear kind of table, which is reversible, but you actually substitute out the bytes of data. Okay? You then pass it through shift rows, which is just rotating the rows. Okay? You shift the rows around. Then mix columns, which isn't actually mixing the columns around, it's passing it through a linear transform matrix, and you just do the multiplication all the way down. But it's reversible. Okay? So it's absolutely fine. Don't worry. And then you add round key. This is the most familiar part of encryption. You do an XOR. Alright? So all of these things come together like this. Okay, and you have these property whereby you get a round key. This is important. So the key expansion, the key expander gives you a new key. The reason you do this is because there's a thing called a slide attack. If you use the same key on every block, then you can abuse collisions in input and output to actually work out what's called the slide of a function. And then you know that this ciphertext has this commonality because it's slid this way and all this other stuff. If you're not familiar with it, there's a book by Jean-Philippe Aumasson, Serious Cryptography. I thoroughly recommend it. It's absolutely brilliant. And he covers off all of this in great detail. It's a really good book on cryptographic engineering. It really is a good text. So the key expansion gives you a new key per round. You then perform all these shift rounds. The reason you do all this shifting, by the way, is you ensure that one change in the bit in plain text affects all the other bits, or could affect all the other bits. Okay? So it's a way of making sure that things get a little bit crazy, a little bit chaotic. And then subbytes uses a nonlinear S-box. The reason you want that is otherwise it just becomes a system of linear equations. If they sound familiar, that's because that's what you were solving in high school. You just weren't doing it in a bit field or a binary field. You were doing it in decimal. But it's the same kind of thing. Without some nonlinearness to the whole thing, then you would have a problem. So this is why you have all these things. But the point to really take home is AES is a well-designed cipher. It is hardened and it is well optimized. So how are we going to break it? Simple, he says. To attack it, we rely on the key expansion and the S-box being reversible. By definition, they are. Okay? Because otherwise you wouldn't be able to recover the data. Alright? So what we do is we actually want to get out the 13th and 14th round keys. So what we do is we take our power traces. This kit, by the way, is exactly what I have here. Do feel free to come and have a little look. This is how you kind of measure the power consumption of a device. So you measure you measure this voltage, you know the resistance, okay? Ohm's law then gives you the actual current measurement, okay? The current measurement is then what you use to say that you are using this much power, okay? And you can see here on the red, the power consumption goes up and down depending on what the chip is doing, okay? This is our window in. Okay, the Chip Whisperer has a really nice, Colin O'Flynn, who's a lovely guy, by the way, he actually developed OpenADC as well, I think, and it's included on the board because it works really well. Okay, it gives you a nice high-resolution power trace. So you measure this voltage, that gives you a level of power, you can then get this kind of graph out, and now you understand a lot about the operation of the chip, but you just don't know which bit is which. Okay? And that's what we have to decipher. So we now have this power consumption data. What are we going to do with it? So it's actually quite straightforward. I'm going to cover off DPA and also CPA very briefly. I'm going to demo CPA because it's a more reliable attack. But I'm going to cover it off how it works. First step you do is you work out the key length. All right? The key length affects the number of rounds. So if you have a key length of 128-bit, you will use 10 rounds. The key length of 192-bit, you will use 12 rounds. 256-bit, you will use 14 rounds in AES. Okay? That's important to know, because otherwise you're going to get everything wrong when you actually do the calculations, and it'll just not work. Okay? We're going to look at AES 128, because it's simpler. But the same works. My point is the same works as you go up the complexity. It's the same attack. You just do some different mathematics in the background because you change the number of rounds. That's the only difference. Okay? So what we're doing is we're going to say, right, this is a AES128 key. Have a look. I leave it as an exercise to work out how I know that, but anyway. Now that we've got this, we can target particular keys with our mathematics. What mathematics works in this case, though? How does this actually come about? Let's show you the algorithm. It's actually quite straightforward. So, we know the structure of the encryption, and we also know some plain text and ciphertext. What we don't know is the key. That's what we want. Okay? We make a guess. Simple. We make a guess. And what we do is we go through all possible guesses and all possible plain texts. Yeah? We then say, if this is a correct guess, that would mean that this trace goes into we're looking at the LSB here. This power trace would go into the 0 box, and this power trace would go into the 1 box. Yeah? We make a guess. Now, if the guess is wrong, and it could be, and it usually is, then it will all stay inside this green. Okay? You won't have any outliers. Alright? This is a key point. When the guess is correct, what you find is that many of the traces, and this is why you have to gather multiple traces, many of the traces will have power consumption that will spike at that point. Remember, power consumption is directly correlated to what you're doing on the chip. Right? What that means is that actually you can see these huge spikes come out, yeah? Up and down in the power traces, because these traces are agreeing, and they're agreeing with your guess. Does that make sense? So because your guess is right, you now have part of the key. Right? Do it 16 times, you get a key. Right? And that's how it works. You go over the traces iteratively, and what you do is you just take these measurements and do these things. A related attack is, pwned, by the way, right? The correlation power analysis is a very similar idea. This is a more reliable attack. This is the one I'm actually going to demo for you. Correlation power analysis is using the Hamming weight. Who doesn't know what a Hamming weight is? All familiar? Okay, so the Hamming weight is basically the number of ones in a binary string. Remember, 1 is high. So 1 means you're using power for that bit. So if you measure the power consumption processing certain bytes, maybe the bytes of the key, you might say, then you can get out effectively what the power consumption should be. And then you can check that against your assumptions using, here you use a Pearson coefficient of correlation. This one here, which is just a covariance divided by the 2 standard deviations multiplied together. Okay? If you don't know why, don't worry, that's just for those of you who are technically minded. I'm a mathematician, I make every apology for it. Okay, but what we're doing is we take these measurements and we go, right, we're doing a very similar process. We're taking all possible guesses and we're iterating through them, and we're doing the S-box lookup, but the plain text with an XOR of the key guess. Alright? We then take the Hamming power of our position, and we get the Hamming weight of the Xbox lookup. Okay? Sorry, we assign that into our Hamming power. And we increment the position by 1, and we go all the way through. We then actually take the actual power, and we get all the traces, and we do a comparison between the two. Okay? If the comparisons match, you get something like this in the analysis. Yeah? If you see that, that means that you have a part of the key. That's a correct guess. How many guesses do we make? All of them. Processing power is cheap enough. We just make all the guesses, do some relatively straightforward calculations, and then we can actually get this information out of a chip just by listening to it really carefully. Alright? This is workable. Okay, this is not lots and lots and reams of difficult code. And hopefully now I'm going to be able to show you a CPA attack on AES. Could you just hold this while I type with both hands? Because my elbow's giving out. Thank you very much. Okay, so all we're going to do first is, so for those of you who didn't see it earlier, this is a chip whisperer. Ta-da! This is a target board, a CW308, I think it's called. And all we're going to do is actually measure the power by plugging it in and going into the capture software. Okay? This is what it looks like. So first of all, we just connect to it. That was easy. And then we go to the AES attack. Okay? What this does, if you look at the code, is it just sets it up so that we get some nice traces. It's just setting up the what the clocks are set to, the resolution of the ADC, that kind of thing. Okay, that's all it's doing. It's just a little bit optimized. We could do this without, but these optimizations help bring out the differences in power consumption. So if I press this, you should see there we are, lovely big bright red trace. Okay? Now, if I can show you this is what we're actually doing in the background. We sent this text in, we got this text out, and we expected this. There's lots of expected and given keys because we want to be able to check that what we're doing is right or wrong. So what you would do is you would find the same chip and you would practice the attack on a like for like before you practice on the target. Okay? Because the target usually, with glitching, anything can happen. Sometimes, or measurements, all sorts of things can sort of be different. So you want to reduce these things to known problems. So you fix it on an actual target that is a development board, say, and then you actually do the measurement on the real target, as it were. So, well, all we had to do is just take, I think 50 samples should be enough. And you can see it's wiggling. See a little bit of wiggling? Yeah? That wiggling is the difference in power consumption. Okay? That was it. What we do now is we save it, because that's what we do. I got lots of example traces. Wow, that messed up, didn't it? I got lots of example traces I've been working on, but we'll do test DPA 8, and that's basically that saved. So now what we need to do is move to the analysis software. Okay, so the analysis software is the Chip Whisperer Analyzer. All this is going to do is open up our data set, like that. And here is the CPA attack. So you can go through all the Chip Whisperer code and see how it works. It'll look very similar to the CPA code that I posted earlier. But basically the attack when it runs looks like this. So here it is actually doing analysis. The red is the key I've given it so that we actually know when it's actually found the right key. And apart from one byte, which it's got wrong, it's found the key. If I show you another example that I did just as you were all coming in, because these things are a little bit unstable. There's this data cable, this display cable that's affecting the power on the Chip Whisperer. These things are very sensitive, so you have to sort of try a lot and sort of really get to use with it. If you took 1,000 samples, it would work first time every time. And I've got different data sets, and you'll just see that it just works on the data set, and all the little bit of red comes to the top before we've even got to the halfway point. And there we are, locked in, done, there's the key. Oops, come on, behave. There you go. Thank you. Easy, isn't it? Pwned, done. That's it. It's that straightforward. You tool it up correctly, and you will be able to attack the hardware encryption on a chip just by listening really carefully and understanding how the encryption actually works. Any questions on that, by the way? Yo.
How well does that work when the chip's actually doing something else as well?
The question is, how well does it work when the chip is like multithreading or something? Not particularly well, if I'm honest with you. But again, you're looking for a correlation in power. So if you took more samples, you probably have a better chance of finding it. But this is why you would, but then again, multithreading on microcontrollers is quite rare. So on an Intel chip, this would be a very difficult attack because it's optimized for doing lots of concurrency. But on embedded systems, this works really well. It really does work well. As you saw, that was only 100 samples in the second example, and it's got the key out, and it's giving you those numbers are the confidences that it has from the statistical analysis. But if you check the code, that is the correct key. It's in red because I said to be in red for visual purposes. Cool. So, who thinks that's workable? Who think that works as an attack? Yeah? Most people. It's fully workable. Yes, it came out of a university. Yes, this stuff, sounds academic, but no, it really does work. Okay? And all it requires is a little bit of understanding, fairly straightforward mathematics, but you don't even have to do it yourself. Just get the computer to do it. It's what we invented them for, literally. Okay? So the theory is actually quite sound and hopefully not scared anyone off. No one's running for the door, so I think that is a good sign. What I want to do is now have a bit of a conversation about how we're going to try and fix some of this, okay? Because these things are all very well and good, all right? But what can we do to try and fix it? Well, hopefully a little bit more. The thing we don't talk about in security very much is the when of security, all right? We talk a lot about the how. We occasionally talk about the who, attribution dice, for example. And we talk a lot about the what. Well, what are we going to do? And, how are we going to implement it? But we don't talk about the when. The when of security is really important, especially when it comes to things like IoT, because you have to make certain decisions at different times. Okay? Here's briefly how I start to consider things like OWASP. Right? Just to give you an example of how I process something that is very well known. This is possibly wrong in some people's eyes. That's fine. This is all in context. Okay? This is all for different security postures. But here what I'm trying to do is show you. You do certain things early, you do other things in the middle, and the rest of it you can leave till later. You don't worry about your firewall setup when you're writing it on a laptop for the first time. Okay? You should worry about filtering out things like XSS or injection attacks. Okay? You should worry about a little bit more about sensitive data exposure when you start doing testing on a development server in the back of your office. You shouldn't be worrying about that when it's already made it to production. It's too late. Okay? To give you a sense of how this works in IoT, these are the decisions that you should make and when you should make them. And again, this is open to discussion. Please do argue with me, disagree with me, tell me I'm full of nonsense. But the aim is to say, look, let's put this in time. It is very hard to fix your cryptographic decisions later. If your chip doesn't support proper encryption, then you are going to have a very hard time if you find out later you should have had encryption. You're going to have a really bad Tuesday, okay? Right? More than the Windows guys, okay? Right? Secure storage. If you need that, you need to decide on that earlier. Make sure you have a chip with an HSM that does the encryption that you want. Right? Likewise, in pre-production, that's when you should implement a firmware update method. Implement it early, because then you can fix it, because you'll mess it up. It's fine. We all do. Right? These things take iteration. These things take development. But you have to think about these things earlier. Likewise, when you're in production, that's when you should really move to clean up your PCB. Remove the debug ports, please. Because you're making my life so easy when you do that. Okay? And likewise, you have other considerations in post-production. Okay? You are responsible for what are effectively software updates. It is your job as developers to actually go, I make sure my SDK is up to date. Okay? Because there's no Windows operating system or Linux operating system to fall back on. There's no system administrator sitting in the background. You are all of it because you control the firmware. Also, if you can, have a PSIRT, a Product Security Incident Response Team. I've dealt with them. They really do work, I think. When you don't have them, I send you an email, and nothing happens. I found a bug and an error. That's cool. And that's it. You know? Usually it's because they can't fix it, to be honest with you. So here's the Mark C's 3-point plan for IoT security nirvana. It's not going to give you nirvana, I'm very sorry. But we'll try and get you close there. These are the 3 things that I wish all IoT companies did. Alright? First of all, ensure you have a per device secret. Make sure that every device has something unique on it and that is the reference point for things like setting up passwords. Routers have been doing this now for a while, and it does work. Why? Because then a vulnerability is strictly limited to the vertical between the device and whatever it talks to. It doesn't mean that I can then take the attack, copy-paste, and run it on devices laterally. Okay? A per-device secret is really important. Alright? Would that more IoT companies did it? Things Network, for example, will let you have a default API key for your LoRaWAN devices. That is the same encryption key, because it's used in the assessment of encryption, in the setup of the encryption keys, the app session key and the net session key. It will let you have a static app key across all devices. It also doesn't give you any provision for remediating such an issue. You have to do it through the firmware update. Right? That brings me to my second point. Have firmware updates. You would be surprised how many companies, IoT companies, don't do this. Right? They don't give you a way of fixing the problem. More and more are doing it. But I think as a community we need to start saying, well look, you need to do this is important. If you don't do this, you will have a problem. Okay? And also there's example code out there, and it's broken. So we have to go out and maybe find it. Maybe we should be a little bit more proactive as an InfoSec community, but the developers also should have a look at it as well, I think. Maybe make them qualify for a CVE. That might help. That might help. And lastly, make the security problem someone's problem. This is a business issue. This is not a technical issue. The number of times I try and engage with a company about a security issue, and I can't. Why? Because it's just stuck in orbit around the office in emails. Endlessly going round and round, it never lands anywhere. Because it doesn't land anywhere, it doesn't get any kind of, it doesn't get put on Jira, it doesn't get put on any kind of management for fixes, no issues are raised in the Git, so nothing gets done. Okay? But if security is someone's problem, they can have the bad Tuesday, you can take them out for drinks later, it's fine. Okay? But in doing so, you will then actually have a better chance of fixing it. This is a step that things like the IoTSF recommendations don't include. because they concentrate a lot on the tech, which is great. They've got some amazing recommendations for how to secure IoT devices. But I think we need to go further and engage on the business structures as well, because there's certain things that just can't happen unless there's someone who has it as a responsibility. So, Kirchhoffs Principle on IoT. I alluded to this earlier. This is after the talk by Andrew Tierney, where he sort of mentioned this at the end, and I want to say it again because I really do agree with it, okay? Anton Kirchhoff was a Dutch, I think, cryptographer from the late 19th century, and he said, a crypto system should be secure even if everything about the system, except the secret key, is public knowledge. That is the idea, for example, of AES. By the way, don't confuse it with Kirchhoff. Kirchhoff's law of circuits is not the same thing as Kirchhoff's law of cryptography. They're very different things, but they have a confusing spelling. This is Kirchhoff. Remove the K, you get Kirchhoff. The second K, that is. Okay? Just in case you're ever wondering and Googling it later and you don't find it, that's why. Okay? So maybe we can have an ideal of this for IoT. Here's how it might look. Me, 2018. There should be a level of security assured in an IoT system, even if complete compromise of one device is assumed. The point of all these cool attacks, and the point of all these advanced things like bypassing CRP, glitching, getting the firmware out, the problem you have is that they all rely on the assumption that that's not going to happen and trying to prevent it to happen. If you write your code with the assumption that it's going to happen, because it is, then maybe we can improve the security posture from the ground up. Don't forget, the enemy knows the system. Okay? Every time. My name is Mark. I'm better known as Large Cardinal. Thank you very much. I'll take some questions.